Right. Good morning, everybody. Do we have a question about the homework? Anybody have any questions? I seen, a couple students had sent me some stuff, and it's a simple order of operations error in a couple of the questions that I got. So for some of the questions, it asks you to find the standard deviation where it's approximately either range over 4 or range over 6. And of course the range is just a subtraction of the endpoints. Say for example it's from 43 to 35. What we have to pay attention here is that we do the subtraction first and then divide by 4. That is not equal to 43 minus 35 over 4, 35. Everybody see the difference between those two things? Because this one, only the 35 is being divided by 4. Here we need the entire difference to be divided by 4. So you have to make sure and include parentheses on your calculator. Now they are equal with the parentheses. Okay, so simple thing like that. Because we haven't really had to mess with order of operations because they've been basically multiplication and division. We haven't really had to worry about it until this point. Right?
Number 3 on 7.5.
Okay.
I think I have
Let's check it out.
3 and 6.
Question 3. Okay. So let's snip it out. And then what we need to do here is recall the formula for n when we're talking about proportions. All right, it asks us to find the sample size based on this information. So the first thing we need to do is write down the formula, which I believe was n equals z alpha over 2 squared times the quantity PQ over our standard error squared. All right. So that's the 90% confidence interval, right? That's the endpoints for it. So that's not giving us P and Q, but it's telling us exactly what the value is. So basically what we need to do here is find where the middle of that confidence interval is, right? And then we can determine how far we go above and below. So what value is in the middle right here? How would I find out what's in the middle?
Add and divide by 2.
Add them and divide by 2. So to find the center, you would do 0.26. So x bar would equal 0.26. The mean of it plus 0.54 over 2. What do we get? 0.4. So how much do we go in each direction? So our standard error is equal to, so 0.4 is the middle. How much above 0.4 do we need to go to get to 0.54? 0.14. And is that the exact same that we need to go below to get to 0.26? Makes sense. So our standard error is 0.14. Okay? We there so far? All right. Yeah, I didn't do an example exactly like this one in class. So let me look at it real quick. And that, of course, all this makes sense. All this is pretty straightforward. Right? There's our formula that I have written on the board. Then we need to determine the value of alpha, which of course is 0.1 on a 90% confidence interval. So therefore, alpha over 2 will be 0.05. So z of 0.05 will be 1.645. So that's what I'm going to plug in here. And SE, my standard error, is going to be 0.14, so I can go ahead and make that adjustment. And then, what was it, 1.645. So we still need to figure out something about P and Q. And it's the midpoint of the two. So I wrote X bar, excuse me, I wrote the wrong thing over here. This needs to be our P because it's a proportion. Or P hat, right? Because it's our sample P.
Well, my numbers might have been different. I got 0.6, but I bet you my numbers are different.
Oh yeah, yeah, they probably are for the example.
My Q is 0.4.
Right. Half the width of the confidence interval, which is 0.14. The sampling error SE is equal to half the width of the confidence interval. We can find the value of SE by subtracting the lower endpoint from the midpoint, which is 0.14 in this case. So the only thing we really need to figure out for this problem is our P and Q, which is just the median of the 2 points.
So on this problem, it's not 1 minus 0.4 would be Q. Oh, okay, it is.
Yeah. So it'd be 0.4 and 0.6. And there we go. And then what do we do if we get a decimal? How do we round it?
Round it up.
Up. And it says it right there, round up to the nearest observation. So this problem, there's kind of a lot going on, right? There's a lot of assumed knowledge for this problem, definitely. But P is the midpoint, and the error is the distance we move up and down from the midpoint. All right? So let's go ahead and punch that in the calculator, make sure we get the right value. So we have 1.645 squared times 0.4 times 0.6 divided by 0.14 squared. I get 33.135. Is that what you guys got? So it'll be 34. And there we go. Because you always round up, right, if there's a fraction. There we go. So really the hard part here was figuring out how to come up with our SE, right, the standard error. So P is going to be whatever this value is, which really we called it P hat in our confidence intervals, right, because it was the sample proportion. Okay. The other ones give you a little more information than that, right? 95% confidence interval, 6 unit in width. It gives you your sigma right there. So this one's pretty, just kind of plug and chug through this one. All right. Oh, and then it asks you, do you have sufficient funds because your budget's this? So it's basically asking you, is it more than 150 samples or less? Right? Isn't that kind of what the question is? Because it costs $10 for a sample. And you have $1,500, so that means you can make 150 samples. If n is greater than 150, you would say no. If n is less or equal to 150, then you would say yes in this case. All right? And it gives you right here the width. Okay. So same. N equals 9 like n, so it actually tells you here, and it asks for the confidence level. All right? So, of course, this one still has a view and example stuff as well. All right. Same stuff. A gigantic warehouse stores approximately 50 million empty aluminum beer and soda cans. Recently a fire occurred. The smoke from the fire contaminated many of them. A statistician was hired by an insurance company to estimate P, the true proportions of cans that were contaminated. How many cans should be randomly sampled to estimate P to within 0.08? So that's our SE. 95% confidence. Tells me it's 1.96, right? Is a 95% confidence interval. 1.96. basically 2 standard deviations. All right. All right. So it doesn't say anything yet about P. Right? What is P and Q? And I think it's in this one, you let them both be 0.5, I believe. How does it come up with P? So yeah, so you just let them both be 0.5 if you're not sure. Because remember, that's going to make n the biggest possible, right? So you'd rather just make n huge rather than small. So you just let P, it says, since there is no estimate given for the value of P, the most conservative is a 50-50 split. Any other value, as we saw yesterday, whether it's 0.8 and 0.2, 0.7 and 0.3, it gives you a smaller n. 0.5 and 0.5 gives us the biggest possible n, right? So to be safe, you're better off sampling more cans than less cans. So there's that. So you just plug it into this formula over here, right? Okay. So let's go in and finish 8.1. And then 8.2 and 8.3 is kind of just a or 8.2 is definitely just a continuation of 8.1. And then 8.3, we're actually doing some actual hypothesis testing rather than just talking about it. Oh, yeah, let me mention that I went ahead and moved the 8.1 homework. It's not due tonight by midnight. I just didn't feel comfortable assigning it yet without covering everything in the section. So I've moved 8.1 to be due by midnight tomorrow, along with 8.2 and 8.3. So we definitely should be able to get through all this stuff today. So then tomorrow we'll start on 8.4, probably get halfway through 8.5, and then Thursday we'll finish the second half of 8.5, more than likely, and then start 8.6. Finish 8.6, all right? So we only have 3 more lecture days for the rest of the semester. This stuff we're not covering, right? Section 11. Or Chapter 11, sections from Chapter 11. Okay. So let's go back and talk about 8.1, which is a very dense section. There's a lot going on in here. We talked about type 1 and type 2 error. And I really want to talk about that again. All right, so where did we end? So we hypothesis, then we test a hypothesis. So in any experiment, we'll come up with 2 hypotheses. The null, which we call the status quo, which just kind of means it's how it is already. It's kind of what we already believe. And then the alternative will be basically the opposite of the null. Remember, the null and the alternative have nothing in common. They are mutually exclusive. That's very important. Right? And my example of guilty and not guilty really shows that. Somebody can either be guilty or not guilty. They can't necessarily be both in the court's eyes. Right? So if H naught was guilty, and our alternative would be the opposite of being guilty, which would be not guilty. Right? And then we have H naught is true. HA, or not true, is proven. Let me put that. Because this is what happens in the test. And then over here is the actual H naught and HA. So here's our chart. And I'll go ahead and flip to that in the book as well. See if we can recall. So this is what our test shows. This is what actually happens in the real world. All right? This is what the true thing is. And a lot of times the researcher really has no information about what the actual is. Right? That's why we're testing it, because we don't know what it actually is. So it led us up to this chart right here. So I'm going to stop. Type 2 error. Right here. Let's talk about this chart. And really I want to talk about the errors, really understanding what the errors are. So here's our chart. Notice the top left and the bottom right are correct decisions. That's good. That's what we want to happen. So when we prove H naught, so we show the person's guilty when the person's actually guilty. That's good. Also, when we show that the person is not guilty when they're actually not guilty, once again, that's good. So our top left and bottom right mean our test worked, right? It did what it was supposed to do. Now our errors are a different story. Type 1 error, which we call alpha, and type 2 error, which we label with a beta symbol. So, remember in class we talked about this, how this one's probably the most difficult for society. And just like with our sewer pipe one, right, where we were putting pipes that weren't strong enough, right, we say that they aren't, or that they are strong enough when in fact they were strong enough. No, other way around, right? That's type 2. So type 1 is when they aren't strong enough when we said they were, so that means we could have a rupture of a sewer pipe. Here in type 1 error, this is when we say somebody is not guilty when in fact they were guilty. Right? And then type 2 is when we say somebody was guilty when in fact they weren't guilty. Right? That's why type 2 is the reason why we have to prove beyond a reasonable doubt, because that minimizes our beta. Right? We don't want to prove somebody guilty when they're actually not. So that's why it must be proved beyond a reasonable doubt. So we'll talk about both of these errors extensively. What's important to note here is the probability of B is unknown most of the time to the researcher. We don't know if B is actually occurring. So when we do our testing and we get to the point where our test statistic doesn't fall in the rejection region, which means we would accept H naught, we don't say we accept H naught because that means we would accept this type 2 error as well. We just say we fail to reject H naught. Because look what happens here. If we reject H naught, then we're rejecting the type 1 error, which is good. So we reject H naught, and then we can assume HA is true, but we can't assume H naught is true. We just say we can't reject it. All right? I know, which is kind of weird to think about, but we'll mess with it a lot more in the next sections. All right? So there's probability of alpha, which is basically the tails, which is where our test statistic falls in the rejection region. We call it the rejection region because we reject H naught. Right? So if it falls in the rejection region, we reject H naught and assume HA is true, which isn't, there's no problem. That's the correct decision. We're not assuming any type 2 error. Right? If we assume H naught is true, then we are assuming some of this type 2 error as well, which we don't know the probability of, which is stated right here. Be careful not to accept H naught when conducting a test of hypothesis, because beta is almost always unknown. That's the probability of type 2 error, which in our pipe problem would have been, we said it wasn't strong enough when in fact it was. Right? If the test statistic does not fall in the rejection region, it's better to state the conclusion, insufficient evidence to reject H naught, or we could say we fail to reject. So we can either say it's not true, or we can say we don't know if it's not true. Right? Those are our two conclusions. And once we see a bunch more examples of this, it makes a little more sense. So right here's where I ended class on Monday, yesterday. We talked about this elements of a test of hypothesis. All right, so there's 7 steps to it. And 1 and 2 are the null and alternative. So that's kind of what your 8-1 homework is, right? Is setting up your null and alternative hypothesis. It gives you a situation. Then you say, well, H naught is the mu is less than 25. And HA is the mu is greater than or equal to 25, or whatever it happens to be. Then number 3, we label our test statistic. We identify it. It's going to be one of 3 things. It's going to be the z-test, the t-test, which is for small sample sizes. So we're going to do the mean of a large sample, the mean of a small sample, and the proportion. So it'll be one of those test statistics. All right? And then we determine our rejection region by determining what alpha is. Alpha is the rejection region. Something we're going to talk about today is the rejection region either being low or above, or just being on one side of our normal curve. We'll call that a one-tail or a two-tail. And we'll see the situations where that happens. Right? So 1 and 2, null and alternative. Right? So 1 is the null hypothesis, which we're not sure exactly what it is. This is just an example, or in general. And then we state HA. So that's what basically your 8-1 homework is. So we identify what our null and alternative hypothesis is. Number 3 is pick the correct test stat, which at first is going to be the z-test. All right, large sample size. Pick the correct test statistic. Number 4 is identify the rejection region. And I'm just rewriting what's up here. I.e. alpha. Alpha is our rejection region. Right? The rejection region is chosen so that the probability is alpha that it will contain the test statistic when the null hypothesis is true, thereby leading to a type 1 error. The value of alpha is usually chosen to be very small and is referred to as the level of significance of the test. Right? 5, we do assumptions, which are going to be different based on each problem, and they'll be explicitly stated to you. Clear statements of any assumptions. So something we could say, assume the population is approximately normal, could be an assumption. Assume the population has a proportion of 50-50. I mean, anything could be brought in right there in number 5. So number 5 is assumptions. If I spell it right. Then number 6, we actually calculate number 3. That's kind of what number 6 is. So number 6 is calculate the test statistic. What do they call it exactly? Yeah. Calculate test statistic. And number 7 is our conclusions. A test of hypothesis can only have one of 2 possible outcomes. There's only 2 possible things that can happen. We either reject H naught or we fail to reject H naught. All right, write those down. And the reason we can't say we accept H naught is because then we're assuming this type 2 error, and we don't know the probability of it happening. Only 2 possible conclusions. One is we reject H naught and accept HA. And the reason we can accept HA is because we do know the probability of type 1 error. That's labeled by our level of significance. Right? If a numerical value of the test statistic falls in the rejection region, right, which is where we found in number 4, we find out where the rejection region is. We reject the null hypothesis and conclude that HA is true. We know that the hypothesis testing process will lead to this conclusion incorrectly only alpha% of the time. So that's why we can go ahead and assume HA, because we know the probability of type 1 error. We know the probability of letting off a guilty person. Which maybe we don't in that specific case, but in all your statistical analysis you will know. And our second conclusion is if the test statistic does not fall in this region, and today that's what we're really going to talk about is identifying our rejection regions. All right? If it does not fall in the region, we do not reject H naught. Thus, we reserve judgment about the hypothesis. Basically, if we can't reject H naught, we need to redesign our experiment and try it again. If we do it over and over again and keep failing to reject H naught, then we can finally, at that point, determine that H naught is true. And actually, there is a way to calculate this beta probability, but we're not going to cover it. All right? So just for your guys' case, it's either going to be rejecting H naught, or part B, we fail to reject H naught. So we're trying to prove that it's not true. We can either say it's not true, or we can say we don't know if it's not true. Right? We do not conclude that the null hypothesis is true because we do not know, in general, the probability of type 2 error, which is beta. All right? Because we don't want to accept H naught, and it was actually type 2 error that led us to it. All right? Because we don't know the probability of beta. We do know the probability of alpha. That's set at the beginning of the test. Okay? So I know it seems like there's a lot going on right here, but once you get in and actually see a few examples and start messing with it, it's not too bad. All right? You just have to make sure and do it. Bless you. You have to make sure and do it in this fashion. You have to do it in this series of steps. You can't skip step 2 and step 3 and go do step 4 and then come back and do step 2. Because step 1 and step 2 lead us to what we're going to do in step 4. And the way we pick the test statistic is basically just the size of the sample. Either Z or T. Right. Okay. So, here's once again our keywords, which haven't changed. They're all exactly the same. We're not going to worry about testing the variance. We're not going to do hypothesis testing on the variance. We're either going to do hypothesis testing on the mean or on the proportion. Okay, we're not going to do it on the variance. So you can kind of ignore that bottom line. But these are giveaways in the question. If it says estimate the proportion, then we know we're talking about P. Okay? If it says estimate the mean, then we know we're talking about mu. As with confidence intervals, the methodology for testing hypothesis varies depending on the target population parameter. Are we trying to find the average or the variance? In this chapter, we develop methods for testing a population mean, a population proportion, and then we don't do the variance. Right? See how it says in optionally? As a reminder, the keywords and the type of data associated with these target parameters are again listed in the accompanying box. And we say P, even though the value of P is most definitely quantitative, I mean, P is a decimal. The information that was given to come up with P is usually qualitative, right? Like the percentage of people who approve of the president. So you either approve or disapprove. That's not a number, right? That's a qualitative measurement. Okay? Does everybody have our steps written down? First, identify H naught and HA. This is basically what homework 8.1 is. Then homework 8.2 is basically the first 4 steps. We pick the correct test statistic, and then we identify the rejection region. Then finally in 8.3, we actually go in and calculate and conclude something about it. All right, so we're doing this in baby steps, small pieces. Okay? Anybody try 8.1? Anybody looked at it? What do you think?
I think the homework seemed a lot easier than the way you made it sound yesterday in class.
Well, it's because yesterday I was talking completely in general, where the homework is a bunch of specific examples, anytime you explain something in general, it's going to be harder to understand because there's not really a hard fact you can get to it. You know what I mean? So that's why I always try to harken back to this pipe bursting thing. Okay? So all we're doing here is we're actually talking about step 4. We are setting up the rejection region. Okay? So this is our previous example. Let me go turn the light off so we can see a little bit better. In section 8.1, we learned that the null and alternative hypothesis form the basis for inference using a test of hypothesis. The null and alternative may take one of several forms. In the sewer pipe example, we tested the null hypothesis that the population mean strength of the pipe is less than or equal to 2,400 pounds per linear foot, against the alternative that the strength exceeds 2,400 pounds per foot, per linear foot. Right? So what we saw here was our type 1 error, which I had erased up here, would be where we accept HA whenever H naught is true. So that's bad in this case. That means we're putting sewer pipe in the ground that's not strong enough. That's bad for everybody. Whereas the type 2 error is not nearly as serious. Type 2 error means we say that H naught is, we accept H naught, right? We say the pipe's not strong enough when in fact HA is true, when in fact the pipe was strong enough. Which doesn't have massive implications, right, for society. It just really hurts the company producing the pipe. Type 1 is a much more serious error. Does everybody kind of see what's going on with that? Okay. This is a one-tailed statistical test. That's because our rejection region only lies to one side. Notice how this value goes all the way down to 0. Basically, what makes it a two-tailed test is if we put not equal to. Because if something's not equal, it can either be small or bigger, right? It could be in either direction. So that's what we're looking for. If our H naught involves an inequality, it's going to be a one-tailed test. If our H naught involves a not equal sign, it's going to be a two-tailed test. Because if it's not equal, that means it could either be less than or greater than, right? So we have to test both sides of our normal curve. This is a one-tailed, and that's why I've called, throughout the whole summer, I've called the ends of the normal curve, I've always called them a tail, right? Look at this tail over here. That's why, because we were leading into this. This is a one-tailed test because the alternative hypothesis specifies that the population parameter, the mean in this example, is strictly greater than a specified value. So notice how HA says it has to be greater than. So our rejection region is only to the right, right? It's only values that are bigger than 2,400. If the null hypothesis had been H naught mu is greater than or equal to 2,400, and the alternative was the opposite, mu is less than 2,400, this would still be a one-tailed test, but now our tail would lie at the left-hand side of the normal curve instead of the right-hand side. Right? Because we're testing for mu being less than a value rather than mu being greater than. Does everybody kind of see the difference between those two? The test would still be considered one-sided because the parameter is still specified to be one side of the null hypothesis. Some statistical investigations seek to show that the population parameter is either larger or smaller than some specified value. Such an alternative hypothesis is called a two-tailed hypothesis. Something like the amount of soda in a can, the mean has to be equal to 12 ounces. So the alternative would be it's not equal to. You don't want to have less than 12 and you don't want to have more than 12. So that would be a two-tailed test. While alternative hypotheses are always specified as strict inequalities, so alternative are always specified as inequalities, but the null isn't always. Such as mu less than 2,400 or mu greater than 2,400, or mu not equal to 2,400, which basically means either side. Null hypotheses are usually specified as equalities, such as mu equals 2,400. Even when the null hypothesis is an inequality, inequality just means not an equal sign, right? It's a less than, greater than, such as mu less than or equal to 2,400, we specify H naught mu equals 2,400, reasoning that if sufficient evidence exists to show that mu HA is greater than 2,400 is true when tested against H naught mu is 2,400, then surely sufficient evidence exists to reject mu is less than 2,400 as well. Does everybody kind of see what this is talking about? So it's saying, if we know that evidence shows that it's greater than 2,400, then it doesn't make a whole lot of sense to say that it's also greater than any number less than 2,400. I mean, if it's greater than 2,400, it's going to be greater than any number that's less than 2,400. So this is kind of the upper end of this inequality. Does everybody agree with that? That's kind of what that's talking about there. Right? And it'll be easy to identify what our null and alternative hypothesis will be. Okay? That's really not the hard part with these. It's really making sure that you don't make a mistake in your calculations in the rest of the procedure. Therefore, the null hypothesis is specified as the value of mu closest to a one-sided alternative hypothesis and as the only value not specified in a two-tailed alternative hypothesis, which basically means not equal to. The steps for selecting null and alternative hypotheses are summarized in the following box. So let's take all that mumbo-jumbo we just talked about and put it in a nice, concise format. Here it is. Steps for selecting the null and alternative. Select the alternative hypothesis as that which the sampling experiment is intended to establish. So the alternative is that which the sampling experiment is intended to establish, i.e. the pipe being greater than 2,400. Right? We want the pipe to be strong enough to put in the ground. So there's two types of one-tailed test. It can either be the upper tail, where mu is greater than some value, or it could be the lower tail, where mu is less than some value. And then finally, the two-tailed, HA is not equal to 2,400. So that includes both less than and greater than. Select the null hypothesis as the status quo, that which will be presumed true unless the sampling experiment conclusively establishes the alternative hypothesis. That's why we're trying to say we reject H0 and accept HA. Because we're trying to reject the null hypothesis. That's the purpose of all this. Right? If it doesn't reject the null hypothesis, then we have to do more testing, because all we can do is fail to reject it. We can't accept it. The null hypothesis will be specified as that parameter value closest to the alternative in one-tailed tests and as the complementary value in two-tailed tests. So what's the only value that mu cannot assume in this statement? It could be anything other than 2,400, so therefore H0 would be mu equals 2,400. Complements, another thing about complements is mutually exclusive, right? I've said HA and H0 have to be mutually exclusive. They can't have anything in common. Okay? All right. So here's some giveaways. Does anybody have that written down? So basically for number one, you would put select the alternative hypothesis, the one in which the sampling experiment is intended to establish, and then just put a one-tail upper, and then this is just specific examples, right? That mu could be greater than really any number depending on what we're testing. That's just an example of our pipe test. And two, let the null hypothesis be the status quo, basically what's already assumed to be true. Okay? Which is the average pipe strength is 2,400 pounds per linear foot. So here's our definitions. This is how we know if it's one-tailed or two-tailed. And it'll say it, this will be put like on your homework. It'll give you an HA and an H0 and an HA. And it'll ask you, is this a one-tailed or a two-tailed? So you basically look at these two questions. A one-tailed test is one in which HA, the alternative hypothesis, is directional. Or basically, HA includes an inequality. That's kind of how you guys can remember it. All right, so one-tailed. HA includes an inequality. Which is a less than or greater than sign. And that's exactly what's going on up here, right? In our box right above. Right in the one-tailed test, it shows HA has an inequality. In a two-tailed test, one in which the alternative hypothesis does not specify which way it departs from H naught, whether it's greater than or less than, and is written with the symbol not equal to. So it's two-tailed. Anywhere, if you see the symbol, the not equal symbol, you know it's a two-tailed test. The not equal to symbol. Because that means it could be either greater than or less than. Okay? So we've talked a lot in general. We haven't really tested anything yet. We haven't actually had to get in and do it. Which once you get in and do it, I think you'll see that it's a lot simpler than all this explanation has led it to be. All right? Okay. So here we go. Formulating H naught and HA for a test of a population mean. So let's go ahead and put it together. So here's the problem. A metal lathe, does everybody know what a metal lathe is? Or any kind of lathe? Basically grinds something down. So say if you're making rims on a car, they start with a big block of aluminum, and they put it on like a point, and they spin it around that point to where it carves into the metal. That's basically what a lathe is. It's checked periodically by quality control inspectors to determine whether it is producing machine bearings with a mean diameter of 0.5 inches. So the lathe has to stay sharp or else it won't do its job, right? That's basically what this guy's doing. If the mean diameter of the bearings, so the average diameter of the bearings that it produces, diameters all the way across a circle, right, needs to be 0.5. If the mean diameter is either larger or smaller, so it doesn't just say less than, right? These bearings can't be too small and they can't be too big. This is different than the pipe bursting one, because that pipe could be super strong, right? It just had to be greater than a certain value, right? It could take a 10,000 pounds per linear foot. That's fine. So there wasn't an upper end, there was just a lower end. Here it's both cases, right? It can't be too small, and it also can't be too big. Then the process is out of control and must be adjusted. Formulate the null and alternative hypothesis for a test to determine whether the bearing production process is out of control. The hypotheses must be stated in terms of a population parameter. Here it is. There's the giveaway right there, right? The word mean. Mean is the giveaway. So we want to know if the population of all bearings has a diameter of 0.5 inches, right? Here we define mu as the true mean diameter of all bearings produced by the metal lathe. That's the status quo. That's what we presume it will be. So we go ahead and let H naught be mu equals 0.5. And our unit is inches, right? You could put 1/2 here as well. That's fine. So it's out of control if either of these two things happen, right? If mu is greater than 0.5 or mu is less than 0.5, then the lathe's production process is out of control. Because the inspectors want to be able to detect either possibility, right, whether they're too big or too small, these values of mu represent the alternative hypothesis. Alternatively, because mu equals 0.5 represents an in-control process, the status quo, this represents the null. Therefore, if the null is equal, the alternative is going to be not equal. All right? Does that make sense? So it's kind of a giveaway. It's always going to be the opposite. Right? These two are complements of each other. If mu is 0.5 or it's not 0.5, that's basically every measurement that the bearing could be. Now, of course, you'd have to stop at 0, right? Because the bearing couldn't have less than a diameter of 0. That doesn't make sense. But those are definitely complements of each other. They have nothing in common. Right? Would you guys agree with that? So is this going to be a 1 or a 2? 2. 2. And it says it right here, of course. So this is going to be a two-tailed test. Now this doesn't give us a confidence interval or anything like that. All we're doing here is simply determining whether it's a 1 or a two-tailed test. That's it. So let's look at the next one, see if we can identify it. So let's look back first. Here, the alternative hypothesis is not necessarily the hypothesis that the quality control inspectors desire to support. However, they will make adjustments to the metal lathe settings only if there is strong evidence to indicate that the process is out of control. Right? So that just means only if we reject H0. That's strong evidence to indicate that the diameter of our bearings is not equal to 0.5. If we reject HA, then we don't necessarily accept H0, we just say we fail to reject H0. So what we would do in that case is we would do the experiment again, but have a higher rejection region, right? We take this level of significance and make it a smaller value. Right? We'd let it be 0.01 or 0.001 so that our rejection region gets a lot smaller. Okay? Or you could do the opposite. Middle lathe. Consequently, mu not equal to 0.5 must be stated as the alternative hypothesis. So let's read this one. Go one more. Cigarette advertisements are required by federal law to carry the following statement. You know, cigarettes cannot be advertised on TV, right? You guys have never seen, other than maybe a NASCAR race where the cars are named after it, which is basically advertising, but cigarettes cannot be advertised on TV. They can be advertised in print, right, in a magazine, and in the magazine they always have this big warning. Warning, the Surgeon General has determined that cigarette smoking is dangerous to your health. However, this warning is often located in inconspicuous corners of the advertisement and printed in small type. Right? Wouldn't you guys agree with that? They don't make it the headline to the advertisement. Right? They got somebody sitting on a beach chair with a big palm tree, smoking a cigarette, and then down in the very bottom right corner they have this little warning. Right? However, this warning is often located in inconspicuous areas. Suppose the FTC, the Federal Trade Commission, the ones that regulate any type of communication amongst stuff that we're going to buy and sell, claims that 80% of cigarette consumers fail to see the warning. Now, I don't know if that's because it's so small or because they choose not to look at it. Probably a little bit of both, right? But they go ahead and just say 80% don't see the warning. A marketer for a large tobacco firm wants to gather evidence to show that the FTC's claim is too high, i.e. that fewer than 80% of cigarette consumers fail to see the warning. Specify the null and alternative hypothesis. So what's the status quo here?
Less than 80%?
Well, that's actually what they want to prove. That's what this company wants to show. So the status quo is that it's greater than or equal to 80%, because that's what the FTC says is happening right now. What's going on as it already is. That's what the status quo means. So our not alternative hypothesis. Now, is this going to be mu or p? P, it's the proportion. It's absolutely the proportion. So our alternative hypothesis would be P is equal to or greater than or equal to, which includes both, 0.8. And our H naught, or our HA, excuse me, would be P is what? Less than 0.8. Because that's what they want to prove. They want to reject H naught and accept HA. And notice it doesn't matter if I had put equal to 0.8 or greater than or equal, because I'm trying to show that it's less than the lower hand endpoint. So I don't care if it's, if the actual status quo is 90% or 95%. I'm just trying to show that it's less than 80%. So the alternative hypothesis is really the important one here. Okay? The marketer wants to make an inference about P, the true proportion of all cigarette consumers who fail to see the Surgeon General's warning. In particular, the marketer wants to collect data to show that fewer than 80% of cigarette consumers fail to see the warning, i.e. P is less than 0.8. Consequently, P is less than 0.8 represents HA, and P equals 0.8 represents H naught. You could put greater than or equal. Does everybody agree that this includes 0.8 as well? Right, when I say greater than or equal to? So I don't really care if P is greater than 0.8. What I want to show is that P is less than 0.8. So that's why they have equals. You could write it as equals. It doesn't really matter. Okay? Because this is the lower end of this. Right? This number could actually be anywhere from 80 to 100 in actuality for the FTC. And there it is. So it's either equal to 0.8, which in this case I'll go ahead and just put 0.8 since the FTC explicitly says equal. If it would have said up here, if it would have said at least, right here, if it would have said, suppose the Federal Trade Commission claims that at least 80% of cigarette consumers, then it would definitely be greater than or equal to. But since it says explicitly 80%, we can go ahead and just make it equals. But what's important is setting up HA, because that's what's going to identify our rejection region. Okay, so we have to make sure we set up HA correctly. Okay? Because remember, type 1 error is in the bottom column of that chart. Whenever a claim is made about the value of a particular population parameter, in this case P, in the previous example it was mu for the diameter of the bearings, and the researcher wants to test the claim believing that it is false, the claim value will represent the null hypothesis. So the null is kind of the status quo. That's what's already being accepted. And the person that works for Winston or whatever, right, for Marlboro, wants to show that that's not true. Now, we can't do this hypothesis test as of right now because it hasn't given us a level of significance. It has to give us an alpha, all right, in the problem. There's no alpha here, right? It hasn't said test it to 80% confidence or 90% confidence or 99% confidence. So all we're doing here is just simply setting up 1 and 2, right? We're just setting up our H naught and HA. So let's go, let me look at April. So let's look at this one. So it said look at 15. So all we're going to do here is set up our H naught and our HA. Let's see if we can do it correctly. Right? So it says DNA reading tool for quick identification of species. A biologist and a zoologist at the University of Florida were the first scientists to test the effectiveness of a high-tech handheld device designed to instantly identify the DNA of an animal species. That's pretty cool if you think about that, right? What if there was a device where they can come in and touch your skin and know exactly what your DNA was? Right? You know, as of now, they got to take your blood and run it through a bunch of tests, and it takes a long time to get the results back. I mean, this would make a police officer's job a lot easier, right? If they could take somebody out or put them in right away, right? Say they are a suspect or they're not. Identify the DNA of an animal species. They used the DNA reading device on tissue samples collected from mollusks with brightly colored shells. So they took tissue from different mollusks with brightly colored shells, right? Which are oysters, or there's a bunch of different kinds, right? The scientists discovered that the error rate of the device is less than 5%, which is way too high to use in a criminal trial, right? Yeah, that number would have to be somewhere around 0.01%. Set up the null and alternative hypothesis if you want to support the findings. the scientists discovered that the error rate of the device is less than 5%. Now we want to support the findings. So that means we want to accept the alternative hypothesis. Remember, you cannot accept H naught. So we want to accept this happening. All right? So what is this, P or mu? First of all. P. Why? How do you know?
Because it's percentage.
And it says, yeah, percentage, and it's got this word right here, right? Rate. That's one of our giveaways. And down here, percent. So in both cases, we would have to know it's P. So I'm going to go ahead and write P for my H naught and my HA. Now it says we are trying to support their claim. Remember, the alternative is the only thing we can say is true. We can't say the null is true. We can just reject it or fail to reject it. So would HA be less than 0.05 or would H naught be less than 0.05? What do you guys think? I know I'm definitely going to have 0.05 over here. Would I put not equal to here?
Less than.
Less than. In which thing? The alternative or the null?
The null. Right?
Well,
Because that's what you're trying to prove?
yeah, but you can't prove H naught. Remember, we don't accept H naught. We can only reject it or fail to reject it. HA we can accept. Does that make sense what's going on there? So the thing we're trying to support will always be the alternative hypothesis. So let me go back to that box. Right here. Right here. This is the important thing. Whenever a claim is made about the value of a particular population parameter that the researcher wants to test the claim, believing that it is false, so we're actually doing the opposite, right? We want to test it believing that it's true. So if we want to test it being false, we would let that be the null hypothesis. So if it's, what's false if they're claiming that it's less than 0.05? Greater than, right? Or equal to. So we're trying to say that what they said, that it's wrong 5% of the time, is false. We're trying to test that claim. So that's going to be our null. So our HA would be less than. And I think this one would actually be the or equal to down here. And the reason is because of our conclusions. We can accept HA. We can never accept H naught. All we can do is reject H naught or fail to reject H naught. Whenever a claim is made about the value of a parameter, in this case P, and I want to test it, believing that it is false, so I'm going to go ahead and say these guys don't know. This DNA reading tool is incorrect more than 5% of the time. So what I do is I want to test this claim that they say it's correct less than 5%. So I want to test that claim by saying it's more than 5%. That's my null hypothesis. My alternative would be this one. Okay? And you could put equal to 0.05. It doesn't really matter. Because if it's 0.06, that's greater than 0.05. Right? Really, we're just testing the low end. Is this a one-tail or a two-tail? Definitely a one-tail. We're just testing the low end. All right? Now, if this would have said, the scientists discovered that the error rate is exactly 5%, then that would be a two-tailed test. So I would say not equal and then equal. All right? And as we mess with these a little bit more, we'll wrap our mind around exactly what it means. Let's go back and look at a couple more examples, though. So we talked about this one. Okay, here we go. I want you guys to write these pictures down. Rejection regions corresponding to one- and two-tailed tests. So if our alternative hypothesis has the form, the parameter is less than some value, then notice how alpha is just the left tail. I want you guys to write these three pictures down. So we can have what's called the lower tail. This is the lower tail test. And these values represent the amount of area under the curve. Over here is 0.5. This area is alpha, so this area is going to be 0.5 minus alpha, right? Minus what's in the tail. That's just like finding the z-score stuff, right? Exactly. If we have the form where our alternative is greater than some value, so for our DNA testing problem, it would be this one, right? And then we have our two-tailed test form of the alternative being not equal to 0.5. So they're both alpha over 2. And this area is 0.5 minus this area, which is alpha over 2. This area is 0.5 minus alpha over 2, which is that area. So that gives us what that value is. So what the arrows represent is the area under the curve. Notice if I add all three of these together. If I add alpha plus 0.5 minus alpha plus 0.5, you get 1. Right? Because the alphas cancel out. And you'd get 0.5 plus 0.5, which is 1. In all three cases, if I added together all of these things, I would get exactly 1. Which is what's supposed to happen. That's supposed to be the area under the curve. So you can go ahead and label this as lower-tailed. This one's upper-tailed. And this one is two-tailed. And then here's a box that talks about what the z value is at each of these points. So remember, for this one, the two-tailed is like the 95% confidence interval that we saw. So z was 1.96, right? Z alpha over 2 is 1.96 for 95%. But these ones, alpha is just to one side. So this is like a percentile. Right? Because stuff lies below it, and then 5% lies above it. And then here's the common values right here. So these are the ones we've seen already, right? These are the ones we've used a lot. So what these mean is, when z is negative 1.28, that means exactly 10% of the curve lies below 1.28. And 90% of the curve lies above 1.28. So this number, z, is greater than 1.28. 1.28 would be the 90th percentile. Because that means 90% lies below it and 10% lies above it. And then if it's two-tailed, it basically splits this 0.1, where 0.05 is in one side, 0.05 is in the other. And notice this is our values for our 90% confidence interval. So everybody write all, 6 of those values down? So notice if it's lower-tailed, it's just the negative of if it's upper-tailed. So if our statistic lies within these regions, then we would reject H naught and accept HA. We would accept all our alternative hypothesis.
Say that again.
if the Z statistic, once we calculate it, which we haven't even done yet, if, say, we got, if we're doing this test and we set up our rejection region to be this, and I plug in my sample mean, and I get, say, Z is negative 1.6, that definitely lies in this interval, right? Because 1.6 is less than that value. So that means we would accept the alternative hypothesis. We would reject H naught and accept HA. Because these are our rejection regions. So if our statistic, which is what we do in step 6, is we calculate the test statistic, if we find it and Z lies within these rejection regions, then we would reject H naught and accept HA. Because it says it right here, alternative hypotheses. And then we'll see an example where we're finally put all this stuff together. And notice in the two-tailed tests that Z is bigger, right? We're more standard deviations away from the mean. That's because the rejection region is split between two places. It's not just in the upper tail or the lower tail. This alpha being 10% is split between the upper and the lower. So that means Z has to be pushed out farther to the right, and Z has to be pushed down farther to the left. That's why I stress the Z's so much, right? The Z scores, the testing on the Z scores. I mean, this chart right here talks a lot about it. Right? If you don't understand the Z score stuff, knowing what's going on here becomes extremely difficult. This is our 99% confidence interval, or our 99th percentile. Basically, if you're in the 99th percentile, that's this one. Right? That means 99% of the area lies below 2.33, and 1% lies above. This is the middle 99%. So 0.5% lies below, and 0.5% lies above. Okay? Everybody have those written down? And this is on page 358 as well. You go ahead and note that in your notes. Okay. Because these are the alphas that we use most of the time. We don't really use other alphas. We either use alphas 0.01, 0.05, or 0.01. We don't really mess with any other ones. So as long as you remember these, you'll be fine. Well, not necessarily remember, understand. Right? The effect of drug and alcohol on the nervous system has been the subject of considerable research. Right? This is basically how they determined that 0.08 got you a DUI, because at that point it had a significant effect on the nervous system. Right? Suppose a research neurologist, which is somebody that studies the brain, is testing the effect of a drug on response time by injecting 100 rats with the unit dose of the drug, whatever it happens to be. Subjecting each rat to a neurological stimulus and recording its response time. Right? Now, something you'd have to do here is she is determine what the response time is without the drug, right? So there's kind of a baseline for it. But they don't do that here for this hypothesis test. The subjecting each rat to a neurological stimulus and recording its response time. The neurologist knows that the mean response time for rats not injected with the drug, there it is, the control mean, is 1.2 seconds. She wishes to test, so that's our status quo. Does everybody see that? That's what it's already assumed to be. So that's going to be our H naught. H naught is going to be mu equals 1.2. She wishes to test whether the mean response time for drug-injected rats differs from 1.2 seconds. So does that mean it can be greater than or less than 1.2? Absolutely. So what would our alternative hypothesis be? What's going to be the symbol between? Not equal to. Notice how the parameter is the same in both places, and even the value on the right-hand side of the symbol is the same. The difference with these is what's in between. What's the operator? So our null is that it's equal to 1.2. The alternative, the thing that she's testing, is whether it differs. She wants to know whether it's less than or greater than. She just wants to know if it differs. Now, if it would have said she wishes to test whether the mean response time for drug-injected rats is less than 1.2 seconds, then we would put less than right here, and it would become a one-tailed test. Everybody kind of see what's going on there? Now we're actually given an alpha. Right here, we are given an alpha of 0.01. This is the first time we've actually seen an alpha in these questions. The keyword mean in the statement of the problem implies that the target parameter is mu, the mean response time for all drug-injected rats. Since the neurologist wishes to detect whether mu differs from the control mean of 1.2 seconds in either direction, that is less than or greater than, we conclude a two-tailed statistical test. Following the procedure for selecting the null and alternative, we specify, and I don't want to give away too much right here. Okay. We specify the hypothesis that the mean differs from 1.2 seconds, since determining whether the drug-injected mean differs from the control mean is the purpose of the experiment. The null hypothesis is the presumption that the drug-injected rats have the same mean response time, and then the alternative would be that they don't have the same. So there's the setup. H naught and HA. So we've done step 1 and step 2. Step 3 is pick the correct test statistic. What's our sample size here? Is that big enough to use Z? Yes, so we would use the Z test because we're testing the mean with a large sample. So we would use the Z test here. Absolutely. So this is 1. So the way you would do these problems is you call that 1, you call it 2. Number 3, you'd put the Z test. My marker's running out of juice here, sorry. Number 4 is identify the rejection region. Right? Which we can do now because we were given alpha. Is this a 1 or a 2-tailed test? 2. So which one of these values are we going to use? We're definitely going to use the bottom row, right, because alpha is 0.01. We would use this one, right? This is our rejection region. So number 4 is our rejection region. That means Z is less than negative 2.575, or Z is greater than 2.575. Sorry, my marker's kind of running out of juice here. I'll bring a new one tomorrow. Is everybody following along kind of how this is working? What's number 5? Assumptions. There's really not any assumptions here for this particular problem. We'll assume that it's normal because of our sample mean will be normal because n is greater than 30, right? So there it is. The test statistic measures the number of standard deviation between the observed value x bar and the null hypothesis value of mu equals 1.2. The rejection region must be designated to detect a departure from mu equals 1.2 in either direction. So we will reject H naught for values of Z that are either too small, less than negative 2.575, or too large, greater than 2.575. The only way that I knew to pick these numbers was it was given to me that alpha was 0.01, which is pretty significant, right? 99%. To determine the precise values of Z that constitute the rejection region, we first select alpha, which was given to us, the probability that the test will lead to incorrect rejection. And it doesn't give us the sample mean. Then we divide alpha equally between the lower and upper tail of the distribution of Z, as shown in figure 8.5. In this example, alpha is 0.01, so alpha over 2 is 0.05, is placed in each tail. The Z values that correspond to the area being 0.05 in each tail are negative 2.575 and positive 2.575. Assumptions. Since the sample size is large enough, the CLT will apply, and no assumptions need to be made about the population of response time measurements. The sampling distribution of the sample mean of 100 rats will be approximately normal, regardless of the distribution of the individual rats' response times. Now, we haven't got to number 6, because it hasn't given us our sample X bar. Right? It hasn't said, of those 100 rats, the average response time was blank. That's where we would go in and actually test. And we'd plug it into the Z statistic, which it isn't given to us in this problem. Oh, and there it is. So it went ahead and computed it, and after it plugged in the response time, so when we did number 6, it came up with a Z equal to negative 3. Now you guys aren't seeing that because it doesn't tell us exactly what the X bar was. But just go ahead and assume after we plug the stuff into the Z formula, we found Z was negative 3. Does negative 3 lie in the rejection region? Is it in either of these intervals? Yes. Right? Negative 3 is less than negative 2.575. Right? Because it's computed to be negative 3. So this is what it was for our experiment. That was the Z value for our experiment. So we would reject H0 and accept HA. Now, would you assume here that the rats have a faster time than 1.2 or a slower time?
Since it's negative.
Well, it's below the left-hand end, so it's probably less than 1.2, right? Because this value was down here. If this value would have been up here, we would expect the response time to actually be greater than 1.2. We see what's going on. Since it fell in this rejection region, we would assume that the drug is working. It's making the rats more responsive, because this number lies in the left-hand rejection region. Now, the way that they came up with this number, they didn't give us the computation for this. All right? They didn't give us what X bar was. The way that they came up with that number was right here, using this. So they plugged 1.2 in here, but we didn't have X bar wasn't given to us, and our sample standard deviation wasn't given to us. If it was, we would have plugged it in and came up with negative 3. Negative 3 lies in the rejection region. Okay? Note that the test is set up before the sampling experiment is conducted. The data are not used to develop the test. Evidently, the neurologist wants to conclude that the mean response time for the drug-injected rats differ from the control mean only when the evidence is very convincing. That's because alpha is so small. That means the probability of type 1 error has been minimized. Right? It's only 0.01. Alpha has been set quite low at 0.01. If the experiment results in the rejection of H0, which it did, she can confidently conclude that the mean response time of the drug-injected rats differs from the control mean because there is only a 0.01 probability of a type 1 error. Once the test is set up, the neurologist of example 8.3 is ready to perform the sampling experiment and conduct the test. The hypothesis test is performed in the next section. Question? So you want this alpha to be as small as possible, this probability of type 1 error. So she set it pretty low. 0.01 is a pretty low alpha. Okay? So that's the end of 8.2. So all you're going to do in 8.2 is set up H0 and HA, identify the Z statistic, and identify the rejection regions. You're not doing 6 and 7 in section 8.2. All right? You're not calculating the test statistic, and you're not making a conclusion. That's what 8.3 is for. Okay. Let's look at 8.3. Got about 20 minutes left. So 8.3 is basically doing 1 through 5 and then including 6 and 7. So we're actually doing a hypothesis test for a population mean when the sample size is large. That's why we're using the Z statistic. When testing hypothesis about a population mean mu, the test statistic we will use depend on whether the sample size n is large or small. If it's small, we'll use the T statistic. Right? If it's less than 30. And whether or not we know the value of the population standard deviation, sigma, which we need for Z, we don't necessarily need for T. In this section, we only consider n greater than or equal to 30, the large sample. Because the sample size is large, we can go ahead and assume the central limit theorem, which makes our life a lot easier. All right? Then we know x bar is approximately normal. Consequently, the test statistic for a test based on a large sample will be based on the normal Z statistic. Although the Z statistic requires that we know the true population standard deviation sigma, this is rarely, if ever, the case. However, we've shown that in Chapter 7, if n is large enough, the sample standard deviation S can be used in its place. So this is all kind of review, right? Stuff we've already talked about. Deviation S provides a good approximation to sigma, and the Z statistic can be approximated as follows. Z is approximately our sample mean minus our population mean, the value we're actually testing. Notice how they call it mu naught. So mu naught in this case would be 1.2. So mu naught is the status quo mean. It's the population mean. Divided by S over square root of n. So nothing new there, right? Formulas we've already seen. Where mu naught represents the value of mu specified in the null hypothesis. So in our rat example, mu naught would be 1.2. The setup of a large sample test of hypothesis about a population mean is summarized in the following boxes. Both the one and two-tailed tests are shown. So here they are. So this is on page 362. So if it's a one-tailed test, notice how we only really look at HA, right? If HA includes an inequality, it's a one-tailed test. If HA includes a not equal to, then it's a two-tailed test. You'll notice the test statistic is exactly the same. And here they use absolute value symbols. So that means absolute value basically means Z is greater than this value, or Z is less than this negative value. So absolute value is distance from 0, right? So absolute value means both rejection regions. I could have rewritten this number 4 from the previous example. I could have put the absolute value of Z is less than 2.575. And this means exactly the same thing as that. Because Z was -3, the absolute value of negative... Oh, it's the other way around. This is the other way around, excuse me. Greater than. So the test statistic that they came up with was -3, which is definitely in this interval. But if I plug -3 in here and take its absolute value, is the absolute value of -3 greater than 2.575? Yes, because it's just the distance from the mean. So I don't want you guys to get confused when you see this absolute value symbol. Absolute value means either greater than some number or less than the opposite value. Okay? Because we haven't really messed with absolute value very much. This is really the first time we've seen it. Notice for a one-tailed test, it's just a strict inequality, right? It's just strictly less than or strictly greater than. Okay. And then determining what this Z alpha is basically comes from that box on page 356, right? 358. So what number gets plugged in right here for Z alpha or Z alpha over 2 comes directly from this box. That's when you set up your rejection region. So this is the absolute value stuff. This could have been written as the absolute value of Z is greater than 1.645. This could have been the absolute value of Z is greater than 1.96. And this could be the absolute value of Z is greater than 2.575. Those are all synonymous. Okay? So if you see absolute values, you should automatically think two-tailed. Okay? Absolute value denotes a two-tailed test. Because if you're 10 miles from Portales, I mean, there's a lot of different places you could be that is 10 miles from Portales. Right? There's a big circle that goes all the way around us. Basically, I could create a circle with a radius of 10 miles. Anywhere on that circle, your distance from Portales will be 10. Even though in one direction it might be a negative number, in one direction it might be a positive number. Right? If I was going to let Portales be 0, that direction go negative and this direction go positive. Okay. So 362. So large sample test of hypothesis. So notice this is basically step 1, step 2, step 3, and step 4 are listed right there. Step 1, step 2, step 3, and step 4 are listed right there. Now it doesn't say anything about assumptions. We obviously haven't done any type of calculation and there's no conclusion here. So you go ahead and write in your book if you want. Print this page out. 1, 2, this whole thing is 3, whether sigma is known or unknown. And then our rejection region is step 4, right? Which is right here. So just restating stuff we've already messed with. All right? Conditions required. So what do you think my sample has to be drawn? What method? How do I need to draw my sample? Randomly, first of all, right? So conditions required for a valid large sample hypothesis test, which are exactly the same conditions as for a large sample confidence interval. 1, it has to be drawn at random, and 2, the sample size has to be greater than or equal to 30. That's how it is for our small sample hypothesis test and our large sample hypothesis test for P. All 3 of them involve our sample being selected at random. Very, very important. Remember, for a small sample confidence interval, what was our condition 2? Does anybody remember? For a small sample confidence interval, the population had to be what? Approximately normal. Right? Yeah. The population itself had to be normal in order to use the T statistic. Very good. And then for the proportion, condition 1 was the same, random sample. Condition 2 was NP had to be greater than or equal to 15, and NQ had to be greater than or equal to 15. Which basically is the same thing as this, right? Which basically means our sample had to be large enough, N had to be greater than or equal to 30. Okay. Once the test has been set up, the sampling experiment is performed and the test statistic calculated. We have not done that yet. We haven't calculated a test statistic yet. The next box contains possible conclusions for a test of hypothesis depending on the result of the sampling experiment. Oh yeah. So here's our conclusions. only one of two things can happen. Either one, the test statistic falls in the rejection region and we reject H0 and assume HA is true. We can assume HA is true because we know this value of alpha. We know this chance of a type 1 error. Remember that the confidence is in the testing process, not the particular result. Because the result could have been messed up just by simple sampling variability, chance error. So one conclusion is we reject H0. The other one is we conclude that the sample experiment does not provide sufficient evidence to reject H0 at the alpha level of significance. Generally, we will not accept H0. You can accept HA, but you cannot accept H0, all right? Because we don't know beta, the probability of type 2 error, which is covered in section 8.7 that we're not covering, all right? So only one of two things can be your conclusion. You either reject H0 or you fail to reject H0. Okay? So let's go back to our rat experiment. Refer to the neurological response time test set up in example 8.3. The sample of 100 drug-injected rats yields the results in seconds, shown in table 8.3. At alpha equals 0.01, use the data to conduct the test of hypothesis. So we've already done 1 through 4. Step 5, we can go ahead and assume normality, that it's normal because n is greater than or equal to 30. So that's our assumption for number 5. So there's our H0 and HA, which is listed right there, right? H0 and HA. 1 and 2. 3, we're going to use the z-test because our sample size is big enough. We've identified the rejection region, which is here. The absolute value of z is greater than 2.575. So nothing new there, right? Stuff we've already covered. Here's all our data. So this is the response time for the drug-infected rats. Right? So number 6 is to calculate the z statistic. Right? So we're actually going to find it. What is our sample mean? To carry out the test, we need to find the values of x bar and s. So we need to go ahead and find z equal to x bar minus mu, which is actually mu naught, right? It's our mean from our null hypothesis, divided by s over the square root of n. What is this z value? Does it fall in this rejection region? Well, we have to be given each of these 4 pieces. They have to be given to us in order to find z. So that implies that z equals, our sample mean is right here, 1.05. So it's 1.05 minus what was our null mean? 1.2, right? Right here. 1.2. So 1.05 minus 1.2 divided by, what's our sample standard deviation? Once again, this value has to be given to us. It's 0.5. 0.5 divided by what? Square root of 100. Now that is something we definitely can calculate, right? We can punch that into our calculator. And we get z is equal to what? So punch it in. So on 1.05 minus 1.2. And make sure that you do the numerator has to be done first, right? Don't make the same error I showed at the beginning of class with the range. Don't put 1.05 minus 1.2 divided by 0.5 divided by 100. Then it'll only divide that piece. We have to divide this entire difference. Right? So it's 1.05 minus 1.2, which is negative 0.15, divided by 0.5 divided by the square root of 100, which is 10. So we're doing negative 0.15 divided by 0.5 divided by 10 equals. So let's see. There we go. So is that what everybody came up with? Negative 3? Yeah, try it again. Let's make sure everybody can get that.
So I got 0.03.
Yeah, it's because of your order of operations are happening funny. So the easiest way to do it is to just go ahead and put the numerator and denominator in parentheses, just to make sure there's not an error with it. So here's what I'm going to do. So I'm going to do open parenthesis, 1.05 minus 1.2, close parenthesis. So that's x bar minus mu. Divided by, I'm going to go ahead and open a parenthesis, 0.5 divided by second square root of 100. And with this calculator, I have to press to the right so that I put the parenthesis on the outside. And then you get, enter, negative 3. So our z value is equal to negative 3. So what's our conclusion? Does this lie in the rejection region? Is the absolute value of this number greater than 2.575? Absolutely. So therefore, we reject H naught and accept HA. Now the next step would be to see whether it's greater than 1.2 or less than 1.2. That'd probably be the next step in the process. The implication is that the sample mean, 1.05, is approximately 3 standard deviations below the null hypothesis value of 1.2 in the sampling distribution of x bar. Recall from example 8.3 that the rejection region is right here. From figure 8.5, you can see that z equals negative 3 falls in the lower tail rejection region, which consists of z values of z less than negative 2.575. Therefore, this sampling experiment provides sufficient evidence to reject H naught and conclude that at the alpha equals 0.01 level of significance, the mean response time for drug-injected rats differs from the control mean of 1.2. It appears that the rats receiving an injection of the drug have a mean response time that is less than 1.2. How are they able to state this last sentence? How does it appear that it's less than 1.2? Because z falls in which tail?
Lower tail.
The lower tail. So since it falls in the lower tail, we would assume that the mean is lower than 1.2. If it would have fallen in the upper tail, we still would reject H naught, but then we would assume that the mean is greater than 1.2. Okay. So let's kind of read through. 3 points about the test of hypothesis in this example apply to all statistical tests. Since z is less than negative 2.575, it is tempting to state our conclusion at a significant level lower than alpha equals 0.01. We resist this temptation because the level of alpha is determined before the experiment is performed. If we decide that we are willing to tolerate a 1% type 1 error rate, the result of the sampling experiment should have no effect on that decision. In general, the same data should not be used both to set up and to conduct the test. Right? Which means the place where this 1.2 came from should not be the sample that you use to conduct the test. It shouldn't come from the same place. When we state our conclusion at the 0.01 level of significance, we are referring to the failure rate of the procedure. Basically, we're saying that 1% of the time our conclusion is going to be false, not the result of this test. We know that the test procedure will lead to the rejection of the null hypothesis only 1% of the time, when in fact mu equals 1.2. Therefore, when the test statistic falls into the rejection region, we infer that the alternative is true and express our confidence in the process by quoting either a level of significance or a confidence level, which in this case would have been 99% confidence. Although a test may lead to a statistically significant, which is something that, books have been written over what is statistically significant. So that's different depending on what test you're talking about, i.e. rejecting H naught at significance level alpha as in the preceding test. It may not be practically significant. For example, suppose the neurologist tested 100,000 drug-injected rats, resulting in X bar being 1.1995 and S being 0.05. Now a two-tailed test would result in this, which would still lie in the rejection region. Right? Because look, our S is a lot different here. It's 0.05 instead of 0.5. The result at alpha equals 0.01 leads us to reject H naught and conclude that the mean is significantly different from 1.2. However, for all practical purposes, the sample mean 1.1995 and the hypothesized mean of 1.2 are basically the same. Right? Especially if you round it to one decimal place, they are the same. Because the result is not practically significant, the neurologist is not likely to consider a unit dose of the drug as an inhibitor in response time in the rats. Consequently, not all statistically significant results are practically significant. All right, and I'm not going to test you over those two statements. It's just simply saying kind of the validity of the experiment. All right, and these are things that statisticians worry about, it being statistically significant or practically significant. You guys just have to tell me whether it falls in the rejection region or not. That's all I really care about. All right, I'm not concerned whether it's statistically significant or practically significant. All right, and that's it for 8.3. So if you go and look in your homework, 8.2 and 8.3 are in the same assignment. So there's not two separate assignments for 8.2 and 8.3. See, 8.2 and 8.3 is the same assignment. So I've combined 8.2 and 8.3 together. Right? So due tonight by midnight is 8.1, 8.2, and 8.3. So all three of those sections. Basically, the beginning of our hypothesis testing, which we basically spent 2 full class periods, 4 hours discussing, right? Now, we started off class yesterday talking about 7.5, but it didn't take very long. It was basically just a plug and chug, and we even talked about it at the beginning of class today. So tomorrow we're going to deal with 8.4, which is test of hypothesis of p-values, right? So we're going to use the proportion for 8.4. 8.5 is the population when our sample isn't big enough, so we use the t statistic, right? And then 8.6 is large sample population proportion. So 8.4 just deals with what's called the p-test, right? So we'll get into that tomorrow. Right, so I want you guys to come with questions about 8.1, 8.2, and 8.3 tomorrow for class. Okay? And I know there's kind of a lot going on with this stuff, but as long as you take it on a step-by-step basis, the problems take some time, but none of the pieces are that difficult in themselves. Right? You just have to make sure that you put the stuff in the right place. Because if you make a small error somewhere, right? If you assume that this is less than instead of not equal to, that affects your rejection region, so it affects your entire test. Okay? So it's just a lot of small, tedious steps. Alrighty? So between tomorrow and Thursday, we'll cover these 3 sections. Then next Monday, we'll review for the exam. And then next Tuesday will be our 4th exam. Next Wednesday, we'll review for the final. And then next Thursday will be the final. Okay? And remember, your final will replace your lowest exam. Now, if your final is lower than your other 4 exams, it won't replace it, of course. It'll just replace it if it's higher. Okay? So you can make up a lot of ground on your final if you do well on it. Okay? Which is how it should be. I mean, the final is the cap, right? It's showing that you know all the information in the class. All right? And then as we get closer to the end, I'll kind of give you guys a ballpark figure to get what you want to get based on your grade. But I need a little bit more data still before I can give you that value. All right, so I'll create a little formula where you put in your current grade and your desired grade, and it tells you what you need on the final to achieve that grade. But that won't take into account any replacement that happens, because that's a lot more complicated formula. Okay? All right, guys, that's all I got for today. Where's my sign-in sheet at? Up here. Yeah, make sure you sign it before you leave. And see you tomorrow.